can use hammers of various sizes to check for integrity or to look for defects in driven piles, auger cast piles and drill shafts, such as this one. Data looks good. I'm about to prepare the pile for the attachment of the gauges by grinding a smooth surface. I am going to brush away any loose material. Ideally, for a pile of this size, several locations should be prepared to check for local defects. This is to review data that's already been collected. This is to collect new data. This is general pile information, pile number, where we're going to hit it, and the project name. Next pile. More pile information, gauge information, number of blows for the set that's going to be analysed. Let's collect data. After attaching the accelerometer to the pile integrity tester and applying some wax to the base of the accelerometer, this will couple the accelerometer to the pile top to measure pile top motion. I am going to hit the pile top with this hammer to produce an impact. Data looks good. We can also test with non-instrumented hammers, and for larger piles we frequently use larger hammers. Data looks good. Now we will move to another location. Data looks good. To finish the integrity testing of this pile, I will test at the other prepared locations. To see the toe more clearly, we will apply a magnification. The data stored on this memory card from the pile integrity tester can be easily transferred to my computer for further processing using the PIT-W program. Data, import, our project, our pile. As shown here, the raw data from our drill shaft lacks detail, and the record must be enhanced to bring out sufficient detail to allow evaluation. The first step is to apply the magnification function to compensate for the signal reductions due to the soil surrounding the pile. By applying a factor that starts from unity and increasing exponentially with length to a factor of 15 at the pile toe, we now see more detail and can recognize the pile toe. Next, we use the wavelet method to remove high frequency noise. Finally, we apply a filter that removes the low frequency content of the data, which comes primarily from soil resistance effects. The resulting signal contains the same basic frequency as our input pulse, and any remaining reflections come from cross-sectional changes. We then can adjust the scale for plotting and are ready to output our results for the final project report.
The pile integrity tester can be used to demonstrate the differences between a good pile and a pile with a defect. Looking at the lower portion of these two piles, we notice the uniform section for the good pile and a reduced cross-sectional area for the defective pile. A good pile
Here's the good pile with no major positive reflections until the obvious large positive reflection at the pile toe. Here's the process results for the uniform demonstration pile.
testing the pile with a defect.
Before the reflection at the pile toe, we notice a major positive reflection which corresponds to the location of the defect. Here's the process results for the defective demonstration pile.